let's continue talking about curve sketching with another example. Let's see what the sketch of f of x equals 1 over x squared minus 3x minus 4 looks like. Now, we'll start by talking about our intercepts. Hopefully you see there's going to be no x-intercepts because there's no way that 1 divided by any number in the world is going to give us 0. But we could talk about the y-intercept. If x is equal to 0, this goes away, and we're left with 1 over negative 4. So hopefully you see that 0, negative 1/4 is the y-intercept. Now let's talk about asymptotes. So let's see if there's a horizontal asymptote first. So what we're going to do is take the limit as x approaches infinity. Now you can take the limit as x approaches negative infinity. Hopefully by the end of this you're going to see you get the same result. So when we take the limit as x approaches infinity of this rational function here, remember what our trick is? We take the largest power of x in the denominator, which is x squared, and we divide each and every one of these terms by x squared and reduce. So now the limit as x approaches infinity, as x gets really big in the positive direction, 1 over x squared, this goes off to 0. 3 over x goes off to 0. And 4 over x squared goes off to 0. So we have 0 over 1 minus 0 minus 0, or 0. So the limit as x approaches infinity of f of x did approach a single finite value, 0. So that means that y equals 0 is a horizontal asymptote. Which means eventually, as x is getting really big in the positive direction, and the same thing will happen as x gets really big in the negative direction, our function essentially levels off right there at the x-intercept, or at the x-axis. Now let's look at vertical asymptotes. So if you remember, good candidates for vertical asymptotes are where the denominator is equal to 0. So we'll take our x squared minus 3x minus 4 and set it equal to 0, factor, and set the factors equal to 0. So we have two good candidates that could possibly give us a vertical asymptote, 4 and negative 1. But we need to justify whether or not they are vertical asymptotes using the appropriate limit. So we need to take the limit as x approaches 4 from the left and or the right and see if we get infinity. And we need to take the limit as x approaches negative 1 from the left and or right to see if it approaches one of the infinities. So I'm actually going to do all of those. The limit as x approaches 4 from below, coming from the left, means we're really close to 4, but just a little less. So this is a number a little less than 4. Minus 4 would give me a negative. A number a little less than 4 plus 1 would give me a positive. A negative times a positive is a negative, so it's going to go off to negative infinity. That alone shows that x equals 4 is a vertical asymptote, but I'll take the right-hand limit anyway. As x approaches 4 from numbers a little bit bigger than 4, so a number a little bigger than 4 minus 4 gives me a positive. A number a little bigger than 4 plus 1 gives me a positive. A positive times a positive is a positive. We're shooting off to positive infinity. The limit as x approaches negative 1 from a little bit less. A number a little less than negative 1, take away 4 is a negative. A number a little less than negative 1 plus 1 gives me a negative. A negative times a negative is a positive. We're shooting to positive infinity. And the limit as x approaches negative 1 from above. A number a little bit bigger than negative 1, take away 4 is a negative. A number a little bit bigger than negative 1 plus 1 gives me a positive, so that's going to shoot off to negative infinity. And all four of these limits show you that x equals 4 and x equals negative 1 are both vertical asymptotes. So we'll keep that in mind when we're graphing. Now let's talk about where we're increasing and decreasing and find any local extrema. So if you recall, where a function is increasing is where the derivative is positive, where a function is decreasing is where the derivative is negative, and local extrema can only happen where the function changes from increasing to decreasing or decreasing to increasing, and that's at critical values. And critical values are where the derivative is 0 or where the derivative is undefined. So we're going to have to start by taking the derivative of this function. Now, if you look back, I had 1 over x squared minus 3x minus 4. Well, I want to bring that entire denominator up by giving it a negative exponent. Now I don't have to use the quotient rule when I take the derivative, but I can use the chain rule. So when I find the derivative, I'll bring the negative 1 down, leave the inside function alone, take 1 away, but then I have to multiply it by the derivative of that inside function, 2x minus 3. So when I combine this together, this negative 1 and this 2x plus minus 3 stays on the top, and I can bring this down to give it a positive exponent, and there's my first derivative. So now, where is this? So, and then, the negative 1 goes away, and I'll put this back in factored form. That might help us in a little bit. So now I want to know where is this positive and where is this negative. Well, in order to know where it could possibly change, would be at critical values. So critical values are where the derivative is 0. So a fraction can only be 0 if the numerator is 0 and not the denominator. So if I set the numerator equal to 0, I would get 3/2. But also the derivative is undefined, gives us critical values. Well, the function itself was not defined at 4 and not defined at -1. We had vertical asymptotes there. So if the function isn't defined, then the derivative isn't defined. So 4 and -1 are actually critical values as well. So we have 3 critical values, -1, 3/2, and 4. So when I draw out my number line and I label my intervals outside and in between, I have 4 intervals here. And just like we've done in the previous examples, I'm going to choose an x value in this interval, an x value in this interval, an x value in this interval, and an x value in here. And figure out, is my derivative positive for that test value or negative? Whatever holds true for one value in the interval will hold true for all values. So I picked a couple x values that fit in each of these intervals, and now I'll plug them into the derivative. Now look at the derivative. It's negative 2x minus 3 all over x plus 1 times x minus 4 all squared. Well, what do you notice? This entire denominator is being squared, multiplied by itself. So if this whole thing is positive, a positive squared is a positive. And if this whole thing is negative, a negative squared is a positive. So what you notice is that the denominator is always going to be positive. Now, if you think back to the multiple times we've done examples like this, we said when you plug the test value in, the number you get for the derivative doesn't matter, just the sign does. So all we have to actually pay attention to is what the sign of the derivative is. So if I plug in -2, I've got this negative right here. 2 times -2 is -4, take away 3 is -7, so that's negative. We know the denominator is always positive. A negative times a negative is a positive over a positive gives me a positive. So I don't even care what the number is, I just care what the sign of it is. Plug in 0, same thing. This is always negative right here. 2 times 0 minus 3 gives me -3, so I have a negative times a negative, and the denominator is always positive. So the derivative on this interval is going to be positive. Plug in 2, this is negative right there. 2 times 2 is 4 minus 3 is positive. A negative times a positive is a negative, divided by the denominator is always positive, gives me a negative. Plug in 5, this is negative. 2 times 5 is 10 minus 3 is positive. A negative times a positive over a positive is a negative. So on this entire interval right here, the derivative is positive. And on this entire interval right here, the derivative is positive. And on this entire interval right here, the derivative is negative. And on this entire interval right here, the derivative is negative. So from this information, we can determine where the function is increasing, here and here, and where the function is decreasing, here and here. And then we'll talk about local extrema. Local minimums happen when you switch from the derivative being negative to positive. That didn't happen. And you'll have a local maximum where your derivative switched from positive to negative, and that did happen. So we do know that this function is increasing from -infinity to -1 and -1 to 3/2. It's decreasing from 3/2 to 4 and 4 to infinity. There is no local minimum. The derivative never switched from negative to positive, so your function does not switch from decreasing to increasing, but we did have a local maximum at 3/2. And we will need to calculate the y value by plugging 3/2 into the original function. So when you do 1 divided by 3/2 squared minus 3 times 3/2 minus 4, you get -4/25. So we do have a local maximum at 3/2, -4/25. Now let's talk about concavity. So remember, our function is concave up where the second derivative is positive, and we're concave down where the second derivative is negative. So we're going to need to take the second derivative. Now look at this function, this derivative. I went ahead and distributed the negative there. And what do you notice? This is the first derivative, and I'm going to need to take the second derivative. And in order to take the second derivative, I'm going to need to use the quotient rule. So my second derivative will be the derivative of the top times the bottom minus the top times the derivative of the bottom. Notice I have to use my chain rule again over the denominator squared. Now let's clean this up a little bit. I'll distribute this -2 here. I'll distribute this negative here. And let's make this a little bit pretty. And what do we notice? Distribute that negative. Oh, I guess I didn't do that yet, but I will. Here I have negative 2, when I distribute this negative here, I get a positive 2x and a minus 3. Here I have a positive 2x and a minus 3, so together I have 2x minus 3 squared. Now both of these terms have an x squared minus 3x minus 4 in common, so I'm going to pull one out from both of them. Here I'd be left with 1, so negative 2 times one of those left, and here I'm just left with that 2 and that 2x minus 3 squared. Now notice this matches this, there's 4 of those, and I can reduce. Now I'll distribute this negative 2 here, and I'll square this out, 2x minus 3 times 2x minus 3. Then I'll distribute this 2 right here, and then I can combine my like terms, and my second derivative is 6x squared minus 18x plus 26, all over x squared minus 3x minus 4 cubed. So now, here's that second derivative again. I want to know, where is this derivative undefined? Well, we know it's definitely undefined where the function was undefined at negative 1 and 4, and where is it 0? So let's set this numerator equal to 0. Notice I factored out a 2. Well, if you look back at when we did the quadratic function, we said if b squared minus 4ac was negative, then you wouldn't have any real zeros. So when you take b squared, which is negative 9 squared, minus 4 times a times c, you get negative 75. So that means the second derivative is never going to be equal to 0, not in the real number system anyway. So the only critical values are at negative 1 and 4 because that's where our function was undefined. So here are the intervals that go along with that. Pick an x value from each of those, plug those into the second derivative, plug in negative 2, you get a positive. Plug in 0, you get a negative. Plug in 5, you get a positive. So on this entire interval, my function, second derivative, is positive. So it's concave up. On this entire interval, my second derivative is negative, so we're concave down. And on this entire interval, my second derivative was positive, so we're concave up. Now, we switched concavity at negative 1 and at 4, so we have 2 points of inflection. So we can see where we're concave upwards, where we're concave downwards, and that we have 2 points of inflection. Oh, but wait! What did we say about the function? It's not defined at negative 1, and it's not defined at 4, so those ordered pairs don't actually exist, so there's actually no points of inflection. And so now I'm ready to graph my function. So I've got my xy axis here, and let's talk about the information we know. We know we have a y-intercept at 0, negative 1/4, which is negative about 0.25, so right about there, we're going to have that nice y-intercept. We know that the x-axis itself, right here, is a horizontal asymptote. We also know there were no x-intercepts, so we shouldn't be crossing the x-axis anyway. We know at x equals 4, which is right about here, we're going to have a vertical asymptote. We know at x equals negative 1, right about here, we have another vertical asymptote. We know we're increasing from negative infinity to negative 1, so somewhere down here I'm increasing. We know from negative 1 to 3/2, so I'm going to label 3/2, we're increasing again. From 3/2 to 4, we're decreasing, and from 4 to infinity, we're decreasing. We do have that local maximum at 3/2 negative 4/25, so that's going to be about here, right about there, kind of messy there. And we're concave up from negative infinity to negative 1 and 4 to infinity, and we're concave down from negative 1 to 4. So that should be enough for us. We know that we're going to shoot off to positive infinity here, based on that limit, and shoot here to that horizontal asymptote there. And notice that function is increasing, and I did draw it so that it was concave up. So what's going to happen here? We're going to increase up until this maximum right here, and then turn around and decrease there, keeping it concave up on that entire, or concave down on that entire interval. And then we're going to look something like this, where we have that horizontal asymptote and that vertical asymptote, keeping it concave down. concave up on this entire interval. So notice what we're doing from